So transforming quadratics. We're going to talk today about this idea of a parent function. And when we talked about parent functions with linears, it's basically the same concept. They just look different, right? A parent function is the most basic form of the graph type. A parent function is the most basic form of the graph type. We talked about parent functions with linear equations. The parent function is just a perfectly diagonal line. Right? Remember, a parent function looked like this. It was just perfectly diagonal. And we could move it up or down. Or we could even rotate it. We could flip it over, right? We can do those same things with a quadratic. The parent function of a quadratic is f of x or y equals x squared. It's the most basic. Because the definition of a quadratic is that it must be y equals. Is this y equals?
Yes.
Yeah, I mean it's f of x, but that's still the same, right? And it must have a squared. And does this have a squared? So we're good. I mean, that's the basics. Does it have a b value? I mean, yes and no, right? There isn't one in the problem, but if I asked you what is the b value, you would say 0. And if I asked you what's the c value, you'd say 0. Right? I mean, it's all there. The minimal, the basic, the most, the smallest requirements are being met. This is the perfect quadratic. It's what every quadratic aspires to be. So let's go up to graph number 1, spot number 1, and we are going to graph the parent function. So we're going to do y equals x squared. And I'm going to say that this is the parent function. And this space, when I flip this open, this is where I can show my work to get my graphing. The first thing I need to do is negative b over 2a, correct? So in this problem, negative b over 2a, what's my b value? 0. So negative 0 over 2 times, and in my parent function, what's my a value? 1. Negative 0, which is just 0. 0 divided by 2 is what? 0. So my axis of symmetry is 0, so it's perfectly right in the middle. So that's one part of the parent function, right? It's going to be reflected perfectly in the middle. That's the perfect part about it. All right, then we find our vertex, and we find the vertex by substituting the axis of symmetry into the original problem. So y equals, and instead of x, right, x squared, instead of x, I'm going to put my axis of symmetry, which is 0. So what's the ordered pair? What does y equal? 0. So my vertex is at 0, 0, which is also known as the origin. Perfect. So even more perfect, like it's exactly in the middle. Oh, the easy thing to do is to look at the y-intercept, correct?
Yeah.
The y-intercept is the next easiest one to graph. And the y-intercept is the what value in a quadratic? Is the constant, right? The c value, the number that's by itself. Is there a constant? I mean, again, it's one of those yes and no questions, right? Is there a constant? Yes. It's 0. So it's not really in the problem. We have to identify it on our own. But I already have 0 plotted, don't I?
Yes.
Okay, so we have to go to step 4, which is pick one value. What value should we pick? Who can raise your hand? Who can give me a value to pick to substitute? What value should I pick? If my axis of symmetry is at 0, my vertex is 0, 0, what value should I pick to substitute to find my first order pair? Dean? 1. Why did you choose 1? Because it's one space away. It's right next to the axis of symmetry. Dean chooses 1. Somebody else could choose what? -1, right? Why is 1 a better choice for us? Because it's positive. All right, here we go. Y equals 1 squared. We substitute the value of 1 in for x, making my ordered pair 1 comma, what's 1 squared? 1. All right, so I'm going to plot that. I'm going to go over 1, up 1. I need 3, at least 3 to graph. Do I have 3? I only have 2, so I have to repeat that step again. I have to pick another value. You could, but I have to have 3 to reflect, and I only have 2 to reflect. I could pick 2, because it's 2 away from the axis of symmetry. You could pick 3. You could pick 4. What's the problem with picking 4? It's going to get pretty big because you're squaring it, right? So 2 squared. So my ordered pair is 2 comma what? 4. So I go over 2 and I go up 4. I'm going to do one more just because I want this to be the most beautiful graph you've ever seen in your entire life. So I'm going to choose to substitute 3. After all, this is the parent function, right? It's the best version of a quadratic. So what's my ordered pair for 3? 3 what? 3, 9. 3, 9. Then, Ella, what can I do with these ordered pairs? Reflect them over the axis of symmetry. So 3 away, 3 away, 2 away, 2 away, 1 away, 1 away. How do you connect your dots? With a curve. A gentle, artistic curve. Look at that quadratic. Isn't it the most beautiful thing you've ever seen? I mean, it's gorgeous. All right, that is the parent function. That is the function we compare everything else to. It is the beginning function. First function ever. Parent function. Yeah, I mean, it's the... All right, so let's try another one. Why is this a big deal?
I used to watch those come down the street when I was a kid, and like I was scared of them.
Why were you scared of them?
There's a street cleaner. This is the most exciting day of Luke's life.
It's cleaning the street, guys. Like, the street. You can take my spot.
So, what is different between the parent function and this new function that I've written? What has changed? What's the evolution of this quadratic, Julie? The value in front of x. So the a value has changed. And what kind of value is this? A fraction. I mean, more specifically, it's less than 1, right? It's a fractional value that's smaller than 1. Right? Okay. It's smaller than 1, but it's still what kind of number? What kind of numbers are smaller than 1? Decimals, fractions, and negatives. But is this negative? It's a positive value. So I'm going to say this. I'm going to say that a is between 1 and 0. So if your a value fits in that category, between 1 and 0, 1/10, 1/2, 3/4, right? Here we go. Let's graph this one. I'm going to rewrite the problem right here just so that I don't have to keep flipping back and forth. Save myself a little bit of work. Axis of symmetry is the first thing that we worry about. So negative b over 2a again. So negative, and what's my b value? 0. Over 2 times, what's my a value? 1/2. So negative 0 is 0. 2 times 1/2 is 1. So what's 0 divided by 1? Still 0. Then we're going to find our vertex. The vertex is when you take the axis of symmetry and substitute it back into the problem. So y equals 1/2 0 squared, which is 0. So can you make a conclusion? Can you, or a hypothesis, I guess? We'll have to keep testing it. If the b value is 0, well, not everything, the axis of symmetry is 0, right? The b value is determining where your axis of symmetry is. If your b value is 0, it's always going to be split in half at the axis of symmetry, at the y-intercept. Y-axis. Okay, can you do your y-intercept? Is there a c value? No, so we're going to have to substitute. Here's my trick about substituting with fractions. Whatever your denominator is, and in this case it's a, what? 2. This denominator is 2. Whatever number you substitute should be a multiple of your denominator. So my denominator is 2, so I should substitute in multiples of 2. If my denominator was 3, I should substitute in multiples of 3. My denominator is 2, so I'm going to substitute in what number? 2. And then if I substituted another time, what else could I substitute? 4. Or I could substitute 6 or any of those, right? The reason you do that is because if you substitute a value that is a multiple of your denominator, you get whole numbers. You do not get a decimal. And Graphing decimals is terrible, correct?
Yes.
So as long as you you substitute a value that is a multiple of your denominator, you eliminate the decimal answers. So y equals, usually I'd substitute 1 because it's one space away. However, this time I'm going to substitute 2. So I substituted 2. All right, 2 squared. 2 times 2 is 4. Times 1/2 is 2. So my first ordered pair is over 2 up 2. I could substitute 3, but it's not a multiple of my denominator. So this time I'm going to substitute 4, because 4 is a multiple of my denominator. All right, so 4 squared, 4 times 4 is 16, times 1/2 is 8. So 4, 8. I have 3 ordered pairs on my quadratic, my parabola, so I'm going to reflect and connect. So that's 4 spaces, and that's 4 spaces, 2 spaces and 2 spaces, then I'm good. I'll connect them using my great artistic ability, sketching in that curve. What happened between the parent function, which is just perfect and beautiful? What happened when I changed my a value? It got wider, but so do you think it's any a value? The a value in this problem is between 0 and 1. If your a value is between 0 and 1, your parabola gets wider. What if my a value is greater than 1? What do you think is going to happen? What if my problem is y equals 3x squared? My a value is greater than 1. I mean, because in my mind, it's going to get bigger, right? It's a big number. 3 is obviously greater than 1/2, so do you think it'd get wider?
Yeah.
I mean, that's what your brain thinks. 1/2 is small, so it should get smaller. 3 is big, so it should get bigger. Let's test it out. (3x squared). All right, so negative b over 2a. It's almost to the point that I don't have to do this anymore because I've made the correlation. If your b value is 0, what's your axis of symmetry? Every single time, if your b value is 0, what's your axis of symmetry? 0. The b value is what determines your axis of symmetry. And if your axis of symmetry, if your b value is 0, it's 0. Okay, so my vertex, y equals 3 parentheses 0 squared. 0 squared is 0 times 3 is 0. So my vertex is also at 0. Can you graph the y-intercept? What is the y-intercept? 0, so it's already there, right? Plus 0. There's no constant. So we substitute y equals 3 times 1 squared. So my first ordered pair is 3 what? 1 comma 3. Over 1, up 3. y equals I'm going to substitute 2 because I need to have a third ordered pair. So 4 square or 2 squared is 4. 4 times 3 is 12. Oh man, it's off my graph. 2 up 12. Oh. There. Thank you. So reflect, because I now have 2 ordered pairs, or 3 ordered pairs. And connect with my best ability. What happened? It got skinnier. So what's the relationship with A? What does A do to the parabola? What is the A purpose? Makes it fatter or skinnier. A changes the what? The width. The value of A changes the width. Oh, I did write function. The value of A changes the width. And it's the opposite of what you would actually think. Right? I mean, if I was thinking that the A value was 1/10, to me that would be a really tiny graph, right? But it's the opposite. 1/10 is a really wide graph. It's the opposite. The bigger the number, the skinnier it gets. So a parabola with an A value of 5 is skinnier than a parabola with an A value of 3. Conversely, flip that over, the smaller your fraction, the wider it is. But the bigger the number, the skinnier it is. It's the opposite of what you would think. All right, if you would like to glue this so you have one thing out of your way. What's something else you think we could change about the graph or the function? We can move it around. The axis of symmetry moves the quadratic, moves the parabola which way? The axis of symmetry moves the parabola horizontally, left to right. So we already know that the B value determines where it goes. Right? The B value determines left to right. So let's write that down because we talked about that when we were finding all of these axes. The B value moves it left or right. So we can change the width with the A value. The B value moves it left to right. So what does the C value do? The C value
Moves it up and
moves it up and down because the C value is what? The constant, which is the intercept. The C value is going to move it up and down. The C value is going to change it up and down. The vertical change. Okay, I want you to graph these on your own. You can graph. Y equals x squared minus 4. And y equals x squared plus 3. Work at your tables to graph those. Did you guys run into a problem or a new thing? Every other problem we've done had an axis of symmetry of 0. Does this have an axis of symmetry of 0? Every other problem we did had a vertex at 0, 0. Is this vertex at 0, 0? No, this vertex is 0, negative 4. Then I still substitute. So 1 squared is 1. 1 minus 4 is negative 3. So 1, negative 3. And y equals 2 squared minus 4. So 2 comma 2 squared, 2 times 2 is 2. Minus, or no, 2 times 2 is 4. Minus 4 is 0. So 2, 0. And reflect and connect. Those of you that are perfectionists out there in the world, you can do another ordered pair to make it more beautiful. 9 minus 4 is 5, so 3, 5. So in this quadratic, for this parabola, the width didn't change. It's still the same width as that parent function. And they're the same width. What changed was its location. And the difference, the reason it changed, is that C value. If you have a negative C value, where does it go? It moves down. So where do you think this next one's going to go? Above. And why do you think it's going to go above, Dean? Because the C value is positive. So again, negative b over 2a, my b value is 0. So my axis of symmetry is at 0. If your b value is 0, your axis of symmetry is always at 0. Is my vertex always at 0? No. The vertex depends on the problem. You have to substitute to figure out the vertex. Y equals 0 squared plus 3. So my vertex is at 0, comma 3. 0, 3. I already did my y-intercept, my plus 3. I mean, it's right there. I can't do it. I have to pick two numbers. Y equals 1 squared plus 3. 1 times 1 is 1. Plus 3 is 4. 1, 4. Two squared plus 3. So my ordered pair is 2, comma 4 plus 3 is 7. Reflect and connect.